Welcome to today's webinar on potential opportunities for bioenergy by using thermochemical conversion. Today's webinar is being offered as part of the Energy Training for Agricultural Professionals program. My name is Leif Kindberg, and I'm a Farm Energy Specialist with the National Center for Appropriate Technology. Funding for this webinar comes from the southern region of SARE, which is the Sustainable Agriculture Research and Education Program of the U.S. Department of Agriculture. Our speaker today is Dr. Samy Sadaka. Dr. Sadaka is an assistant professor and extension engineer in the Department of Biological and Agricultural Engineering at the University of Arkansas Division of Agriculture. Dr. Sadaka has more than 25 years of active research work in the fields of agricultural engineering and renewable energy. He has established 2 biofuel and bioenergy research and extension laboratories at the Rice Research and Extension Center in Stuttgart, Arkansas. At his research laboratories, he has developed a portable biodiesel demonstration unit, as well as a portable pyrolysis and gasification unit, which he will be discussing today. We will have plenty of time during and after the webinar for questions. You may ask Samy questions directly by clicking on the small hand icon in the upper right corner of your screen. Samy or I will unmute you so that everyone can hear your question. With that, Samy, I'll turn it over to you to start today's webinar.
Thank you, Leif, for your introduction. The presentation today will cover an introductory about potential bioenergy production via thermochemical conversion processes. I will share with you some thoughts about what's the motivation for returning to biorefinery, what are the biomass availability, fundamentals of thermochemical processes, which include gasification and pyrolysis, and what are the challenges we're facing today for gasification pyrolysis conversion process. Are there any good applications that we can utilize today for gasification and pyrolysis? And I'd like to share with you some research activities taking place in my bioenergy labs in Stuttgart, Arkansas. As we all know that we have several factors that motivate scientists and industrial partners to biorefinery from biomass. So what are these factors? They are including the national security. We need to reduce our dependence on foreign oil. We have some issues with environmental quality, like global climate change or higher temperature, acid rain, waste disposal, and also we have excess agricultural production. So we are trying to utilize all this in terms of energy production, and we are trying, these are the factors motivate us for biorefinery. What are some of the energy facts we have? We all know that the United States is the largest consumer of energy use. We are using 105 exajoule. Exajoule is 10 to the power 18 or 100 quadrillion of BTUs per year. So we are using 20 million barrel every day of petroleum oil. That means that we are using huge amount of crude oil every day. We are importing almost 60% of this crude oil, as you can see from the line here, that in 2006 we imported 60% of our crude oil. The proposed United States renewable fuel standards will require domestic supply for 36 billion gallons by 2022. And out of this 36 billion, we need 21 billion gallons must come from advanced biofuel. So how can we fill the gap? We can think about it by you start utilizing biorenewable resources, such as biomass. We have dedicated energy crops on the right-hand side. We have agricultural residues in the middle, and we can have traditional crops for producing fuel. Is this biomass available to us that we can use every year? Yes, we have a study by USDA and DOE saying that total potential excess of biomass production per year can exceed 1 billion ton every year. So this can represent 66% of gasoline demand, more than or 2/3 of our gasoline demand can be produced. It is scattered. We have some areas can show that we have concentrated areas of biomass. We have less areas of biomass, but at least we can think about utilizing crop residues or dedicated energy crops or forest residues and other material for energy conversion. There is no one single energy conversion can be the technology for everything. No, we have several technologies that we can utilize our material based on the feedstock type. So we can have biological or chemical processes, which include anaerobic digestion and alcoholic fermentation. Each of them can produce different type of fuel. Digestion can produce methane. Fermentation can produce ethanol, which is alcohol. Or our presentation today, technologies which will cover thermochemical conversion include combustion, pyrolysis, and gasification. From the name we have, combustion will give me heat source. Pyrolysis will produce bio-oil, liquid oil. Gasification, from the name, it will produce some gaseous fuel. We produce this through a technology or process named Biorefinery. It's a process converting biomass to a marketplace product such as biofuel or biopower or conventional and renewable products. Biorefinery, this concept is very similar to what we have in the petroleum refinery process. We have two major approaches, biorefinery approaches we are using. One is the sugar platform, which utilize biomass, which contain sugar, or using enzymes to convert starch material to sugar, and this sugar can be fermented to ethanol, or thermochemical platform, which include gasification or fast pyrolysis to convert biomass to fuels and chemicals. Sugar platform gained the lion's share previously because many people know how to convert starch material or sugar material to alcohol. Thermochemical conversion process start to gain momentum again, and people start looking deeply since, as I will show in a few slides later, this technology can easily be applied and can convert many types of biomass to useful fuel or chemicals. So as I mentioned, we have direct combustion, we have thermal gasification, and fast pyrolysis. These are the three major thermochemical conversion processes which we'll cover today. Direct combustion is a very old technology. People know it many years ago, and it has many advantages that it's already commercially available technology now, and we can convert many types of dry feedstock to heat. We can burn the material in excess environment of oxygen, and we can produce heat. We have to utilize this heat, and this is one of the disadvantages, that we have to utilize the heat in situ. Some other disadvantage of direct combustion, which include we have penalties related to high moisture content fuel, because moisture content need to be driven off first, and then you can start burning the material. We have also agglomeration. Agglomeration means that the particles in the reactor can fuse together and make a one piece of particle that can affect the gate of the reactor. So this can come from the alkali we have in the biomass. So we call it agglomeration or ash fouling in the reactor. We have relatively low thermodynamic efficiency for combustion compared to other thermochemical conversion process. One of the major topics for our talk today is gasification. So we said about direct combustion, and now we're talking about gasification. What is gasification? It's still a thermochemical process working under 1000 degrees Fahrenheit. We expose the biomass to about 1000 degrees centigrade, and we introduce less amount of oxygen than what we need for complete combustion, for burning. We introduce less amount of oxygen to convert our carbonaceous material to gas, not gasoline, to gas. And this gas include carbon dioxide, carbon monoxide, hydrogen, methane, hydrocarbons, tar, and char. And this is a major chemical reaction for gasification process. I will mention here that gasification process, once it started and once it reached steady state, it can be a self-sustained process. What I mean by self-sustained process? That it can introduce or produce some heat required to gasify the remaining of the material, so we don't need to add external heat source all the time. We need to start the process, and then once the process in a steady state mode, it will be self-sustained process. What are the fundamentals of gasification process? First of all, if I introduce moist material with moisture content, maybe in the range of 20% or 15%. First of all, when I expose this biomass, a piece of wood, to heat, when it has some moisture, the moisture will be released. It will be driven off. And then, second step, porosity of this biomass will increase because you have some volatile matter, volatile gases will be released, and then the porosity of the biomass will increase. And this volatile matter include carbon monoxide, carbon dioxide, hydrogen, water vapor, and some light hydrocarbons and tar. And these gases, when they found the environment required for chemical reaction, they will react together and producing more carbon monoxide or hydrogen. It depends on the environment I have in terms of temperature, pressure, existence of catalyst, or some other factors. And on the right-hand side, you can see the triangle here, the rectangle here, mention that I have endothermic reactions and exothermic reactions. What this terminology mean? I have endothermic reactions mean that some of the reactions required heat. Other reactions are exothermic, which means that they will release some heat. Engineering adjustment will make the requirement heat equivalent to the released heat, and then the process will be a self-sustained process. That's the main idea behind gasification process. So I can start my reactor, and then it will be a self-sustained reactor. So based on that, what are the common types of gasifiers or reactors? We have about three different common types of reactors. From the left-hand side, you can see what we call it updraft, and the middle one is a downdraft, and on the right-hand side, you can see a fluidized bed. The updraft and downdraft share that I'm introducing my biomass from top to bottom. On the updraft gasifier, I'm introducing the oxidant from the bottom to top, it's going upward. And in the downdraft gasifier, you can see in the center here, I'm introducing the oxidant, and the gas will be produced at the bottom. So we are producing producer gas or syngas. I will explain what's the difference between them now. And we are producing char. We are producing tar. On the right-hand side, you will find a fluidized bed. Fluid, it means that we are imitating what happened with fluid. The bed contains sand. As you can see, the shadow area is contained with sand. And this sand, because we introduce oxidant or air or any other gasifying media from the bottom, the sand will be lifted up and down many times, which will increase the heat and mass transfer rate. And then if I'm introducing the biomass from a horizontal auger, the biomass instantaneously will be converted to gas, will be volatiles and converted to gas and char with tar. And because we have the sand in the reactor, the sand will help us in terms, as I mentioned, to work as a heat, increase the heat and mass transfer rate, and also to work as a heat sink, which can contain some of the energy to convert more biomass to gas. Just a schematic diagram of my mobile fluidized bed gasifier pyrolyzer. Starting from the left-hand side, you can see the auger, which enclosed in the hopper to metering the biomass going to the system, and then another injection auger, number 6, which will inject it to the reactor. As I mentioned, reactor contain sand, and then the biomass instantaneously will be converted to gas, and the gas will go through 2 cyclones, number 16, and these 2 cyclones will clean the gas from any particles, from char, from maybe few particles of sand, which will try to escape from the system. So char will be collected in containers number 16, and the cyclone will separate char from the gas stream. And then the gas can go either to be burned out or can be cooled down for more processing if we need to do more refinery. Gasification efficiency, it's a little bit higher than combustion efficiency because we are taking the biomass in a lower temperature and with a lower oxygen environment, and this can produce higher efficiency for gasification process. As you can see that we can expect 90% efficiency based on high pressure and high temperature reactors, gasifiers. We can expect 70 to 80% efficiency from typical air-blown gasifiers. We are measuring the efficiency on a different way by cold gas efficiency, which is the efficiency of the gas divided by the energy in the gas divided by the energy in the biomass. And this can be in the range of 50 to 70% for all our cold gas efficiency. So we can measure the efficiency in 2 different ways. The first is the chemical energy of the solid, of the fuel, and compared to the energy in the gas and also the sensible heat. So in the first thermal efficiency, we are taking the sensible heat into account. In the cold gas efficiency, we take only the energy in the gas. So we have 2 different ways to measure the efficiency of a gasifier. Typically, gasifiers, as I mentioned, can work maybe 750 degrees centigrade, and you can see the temperature line on top is just almost a steady state line. We can expect to produce, as I mentioned, methane, carbon monoxide, hydrogen from these gases, and this can be in the range of maybe 9 or 8 to 9% hydrogen, methane about 6%, carbon monoxide and carbon dioxide in the range of 15 to 20%. Some other lighter hydrocarbons, ethylene, acetylene, and those normally lower than 2%. If I'm introducing air, I can expect 50% of my producer gas can come as nitrogen, which will lead me to say that the gasifying media, the gasifying material, the gasifying fluid which I'm using can be air, which certainly will produce nitrogen in my producer gas, or can be steam. And steam, it means that I'm eliminating nitrogen from my producer gas, which mainly I'm producing carbon monoxide and hydrogen. And that's the main reason many scientists name it syngas, because syngas is the gas contain mainly carbon monoxide and hydrogen. Producer gas is the gas contain all what you can see in the table on our screen. We can use hydrogen for gasification. We can use only oxygen for gasification. And these gases can introduce or produce more higher BTU producer gas, but certainly each of them has its own disadvantage because of the expenses, economical ways, or safety issues. So each type of gasifying media can have its own disadvantage. And also sometimes we need to introduce or to keep maintaining the heat if we are using different type of gasifying media rather than air. The typical BTU or heating value of the gas in the range of 5 megajoule per cubic meter. Let me translate this number to BTU. I'm expecting the gas to be in the range of 125 BTU per cubic feet. Just to give you a comparison with natural gas, it's 1,000 BTU per cubic feet. So the producer gas will be almost about 1/8 BTU compared to natural gas. But it's still coming from a renewable source material, from renewable feedstock, such as wheat straw, rice straw, dried animal manure, or wood chips, or any other crop residues I can utilize for producing producer gas. We have many potential of use of this producer gas. We can take the producer gas, downstream and burn it right away to generate electricity, or we can take it downstream and work on the gas with more chemical reaction, or do more biorefinery, and to produce either hydrogen or alcohol or polymers. So we can work downstream of the gasifier to produce more value-add material. In addition to that, what scientists are looking for currently is to work with more upper stream of the gasifier to enhance the quality of the biomass, because maybe enhancing the quality of the biomass can reduce the tar production. Remember, I mentioned that we are producing 3 major components from gasification. Number 1 is the gas, which is our target for gasification process. Number 2 is char. Number 3 is the tar. Let me start with number 3 now. Tar is a viscous material which I do not like to introduce it to an internal combustion engine because of its viscosity. It will affect the internal combustion engine and make it very difficult to keep it running. So we are trying to eliminate or minimize the amount of tar produced downstream. Second item, which is a char. It has a potential of interest now from many scientists around the world, because we can return back this char coming from crop residues back to the soil, which can work as a soil amendment. So we are not only producing a producer gas, and we are producing some heat, sensible heat with the gas, but also we can produce char, and this can help as a soil amendment, and soil scientists said that it can enhance the quality of the soil, and it returning back some nutrients back to the soil. And also we are producing a material which we like to eliminate or minimize, which we call it tar. Now we can not only produce gas, we can not only generate electricity from syngas, but we can produce more liquid fuel. This technology is not a new technology. Producing methanol from syngas, it's an old technology. And methanol, the alcohol starts with M, needed for all biodiesel making plants. So they need methanol to blend with vegetable oil to make biodiesel. So we can produce methanol from different type of feedstock that we can gasify it, and then downstream we can introduce the carbon monoxide and hydrogen. Those are the main 2 components of the syngas. And then under a certain pressure, temperature, and existence of catalyst in a Fischer-Tropsch reactor, we can produce methanol. As I mentioned, it's an old technology. Another interesting subject, we can produce ethanol. Ethanol, which many years people succeed to produce ethanol from corn through the sugar platform, as I mentioned earlier. But now we can take the syngas, which mainly hydrogen and carbon monoxide, bubble it through a fermenter, and with the existence of a specially type of microorganism capable of converting the syngas to ethanol, they take this syngas, hydrogen and carbon monoxide, they combine them together and produce ethanol. So that's, as I mentioned here in my slides, this technology, it's underdeveloped by a company named BRT, and this company exists in Fayetteville, Arkansas. I like to share with you some of my calculations which I have on some of my fact sheets, and you can find them on University of Arkansas Extension website, that if I have 1 acre of wheat land, how many pounds I'm expecting from wheat straw, and also how can I replace propane by this amount of 1 acre of wheat land. If I have 1 acre of wheat land, I'm expecting to get about 3,000 pounds of wheat straw. And this will replace, if I convert it to syngas or producer gas, each cubic feet is contain 125 BTU. I can replace almost 400 pounds of propane. I want you to remember with me this number, because when I go to pyrolysis, maybe you'll find a different number and we will compare these two numbers later. So I'm expecting to replace 400 pounds of propane if I'm utilizing crop residues or wheat straw coming from 1 acre of wheat land. The second technology I'd like to mention today and share with you is a fast pyrolysis process. Fast pyrolysis, as you can see at the bottom here, I have biomass. I like to expose my biomass to higher temperature, let's say 500 degrees centigrade, compared to gasification. Gasification was almost 1,000, so it's half of the temperature. But I like to apply a high heating rate. It's almost 1,000 degrees centigrade per minute. So I'm exposing my biomass to a high heat rate and to a moderate temperature. And then I'm expecting to have a zero environment of oxygen in my reactor. This will produce 3 major components. Remember, in gasification, my target was, I will show you in the next slide, or the following slide, what looks like this bio-oil. And we are producing char and gas. So if I have 100 pounds of biomass, you expect to produce almost 60 pounds of bio-oil, similar to crude oil, 20 pounds of char, and 20 pounds of gas. So fast pyrolysis process, it's unlike gasification because I need the feedstock to be more dry. I like the biomass to be less than 10% moisture. In case of gasification, I said maybe 15-20% will be okay. I need the biomass meter or less. And also you can see that I need very short residence time, almost 0.5 to 2 seconds for my biomass to stay in the pyrolyzer. I mentioned before that we need moderate temperature up to 500 degrees centigrade, and certainly I need instantaneous quenching of the vapor to convert it to liquid oil. How a reactor looks like, you have the feedstock coming, as you can see, from the left-hand side, and you inject it to a reactor. And in this pyrolyzer, the biomass will not be converted to mainly gas, no, it will be converted to mainly volatile matter and aerosols. And this volatile matter will go through the cyclones to clean it from char, and then instantaneously I will cool down the vapors to collect bio-oil and start storing the bio-oil. I'd like to mention to you that here I have a second layer around the reactor that normally I am heating my system. In gasification, we said that our gasification process, once it's already started and reached steady state, it can stay self-sustained process. But in pyrolysis, I need to maintain the energy source or heating the system, heating the reactor all the time from the surrounding to keep the process running or to keep the pyrolysis process running. So I need to supply energy all the time to the pyrolysis process. How bio-oil looks like, as you can see on the right-hand side, you convert solid biomass, sawdust, or ground wheat straw or rice straw or any other kind of rice hull or even dried poultry litter to crude oil, similar to crude oil. However, I said that my initial biomass started with less than 10% moisture content. We expect that we get between 15 to 30% moisture content in the bio-oil. We are not creating moisture, but some chemical reactions will produce more moisture that will make it about 30%, up to 30% in the bio-oil. Bio-oil is very acidic. The acidity is around 3, so it's very acidic, which means that we have to make sure that when we store it, we have to store it in a certain type of containers because it's because of this acidity. In terms of BTU, the bio-oil can be normally in the range of 11,000 BTU per pound, or maybe 16 to 26 megajoule per kilogram. It's a little bit higher than the original biomass. We are not creating energy, but we're condensing the energy from a solid type of biomass to the liquid, easier to transport biomass and easier to store biomass. We're converting the solid, bulky type of biomass to more condensed to transport biomass. How much bio-oil I can produce from wheat straw, similar to what we did before. If I have the 1 acre of wheat land, still I can produce the same, about 30%, 30 pounds of wheat straw, and this will give me about 566 pounds of propane. Previously, we said about 400 pounds of propane can be replaced if I'm doing gasification process from the same 1 acre, which is produce 3,000 pounds of wheat straw. Why is the difference? Why is pyrolysis oil can replace more propane compared to gasification? Because in gasification, the process is self-sustained. It means that it's consuming some of the energy to keep the process all time running on a self-sustained environment. But in pyrolysis, I am introducing biomass, introducing heat all the time. So that will show us why we have a higher propane replacement from pyrolysis compared to the 400 pounds propane replacement in gasification process. These technologies, however, they are gasification is very old technology. It's 1934 technology, and still we have some challenges with converting biomass to either gas or pyrolysis oil. We have the inconsistency of fuel, because if I'm trying to run my gasifier today for 1 or 2 or 3 weeks on wheat straw, and then later on I need to start utilizing poultry litter or different type of material. So we have inconsistency of fuel, and maybe even within of the wheat, of the straw, of the material, the crop residues itself. We have to process our biomass. I cannot take large pieces of biomass, of wood, and introduce it to the reactor. We have to make sure that it's dry enough and it's grind enough, chopped enough to be handled easier, either for gasification or pyrolysis. We are producing ash, tar, and maybe ammonia or sulfur or particulate, and still, as I mentioned earlier, that the BTU of the gas is almost 1/8 of the natural gas. So it's a low BTU gas still. But certainly, gasification and pyrolysis can utilize a renewable resource, and then I can use them for producing gas or bio-oil, which in other words, I can introduce more jobs to our market instead of transporting or exporting these jobs overseas. So we can build many gasifiers or pyrolyzers and create more jobs domestically here instead of exporting these jobs overseas. Almost gasification can produce a near to zero gas air emission because you are utilizing the biomass to produce gas, and the temperature we are working on in gasification process is lower than the temperature in combustion. So we are not producing too much or higher concentration of air emission gases. So we don't have to deal with these gases to the same extent like what we deal with that in combustion process. The cost of gasification and pyrolysis now is becoming competitive because we have several types of processes which we can work on downstream by producing more value material that can introduce a faster payback for the whole process. So the processes start to be economically visible. Gasification and pyrolysis utilize abundant resources of renewable material, which we can utilize, and we can locally produce our fuel, which can replace some of the fuel we are importing from overseas. So we have the biorefinery approach to convert lignocellulosic biomass to either gas through gasification or to liquid oil through pyrolysis, and to add to the sugar platform. Instead of producing liquid fuel through the sugar platform, we can also produce liquid fuel ready to go to the tank through thermochemical conversion process, and also working downstream with the gas or with the bio-oil. Just to share with you some of the work which I'm developing in my bioenergy lab in Stuttgart, Arkansas, and you're welcome to come and visit at any time, that I have a mobile unit, pyrolysis gasifier unit, based on the fluidized bed technology. And the main idea of building this gasifier pyrolyzer unit, that it can be easy to move from the lab to the corner of the farm to convert biomass to maybe liquid oil through pyrolysis process, and then store the bio-oil on the farm. And then later on, we can work with the bio-oil converted to gas or converted to other type of hydrocarbons, because chemically we can take the bio-oil and do many biorefinery similar to what we are doing with crude petroleum fuel. So my goal here is to take the unit to the farm instead of bringing the biomass to the centralized biorefinery place. And the main idea is to save the transportation cost, and also to handle crude oil or bio-oil. It's a bit easier from handling and transporting bulky material or biomass. In addition to that, I'm working downstream of absorbing carbon dioxide. Remember, we said that carbon dioxide is contaminating our gas, or I mean by contaminating is lowering the BTU of the gas. So I'm trying to absorb the carbon dioxide and also minimize air introduced to the system and maximize steam. So if I maximize steam and minimize air, In other words, I'm minimizing the nitrogen and absorbing carbon dioxide, and hopefully I can reach medium BTU gas. What I succeed to gasify is with this system and similar system like what I have here, is wheat straw to produce our gas, rice straw to produce our gas, poultry litter, or glycerin. Glycerin is a liquid byproduct coming from biodiesel plants. It can be gasified easily in a gasifier like this, and then it can produce hydrogen, and hydrogen can be hydrogen and other gases which in the producer gas can be burned and drive a turbine, and the turbine will generate electricity. So we can just make a biodiesel plant maybe partially independent on the grid. With that, I will turn it back to Leif and ready for any questions.
Thank you, Samy, for that excellent presentation. I just want to remind our listeners that if you'd like to ask a question, please raise your hand, the small hand icon on your menu.
So when you look at the net energy balance on this, it's going to take a fairly good horsepower unit to grind this stuff down, and then you've got the cost of this unit as well. Dollar-wise, what are we looking at totally, and with the energy that we're consuming in order to make this bio-oil, are we gaining much in the whole process?
I certainly agree with what you're saying here, that most of these processes are marginal process if the crude oil or the oil price is down. And the numbers I heard from my colleagues, many of my colleagues, the people working in economical ways, they mentioned that maybe the range of $100 per barrel will make all this way, including grinding and supplying heat for pyrolysis or starting the process for gasification. It will make it more economically feasible. But certainly, if we succeed to find in the future ways that we can reduce the cost for grinding, then yes, it will start maximizing the benefits of any process like this. But certainly, the way we have the system like what we have here, a fluidized bed system, that it's accept different type of varieties of biomass. So we don't have to change any part. If we are using poultry litter or wheat straw or rice straw or wood chips, so we don't have to change anything internally. All what we need to do is more grinding or more preparation of the biomass. But just for comparison, if I look to converting corn to ethanol, I have to take the corn and do some grinding and treat it with enzymes to convert the starch to sugar. So each process has its own techniques, or the feedstock needs its own preparation for making the technology in optimizing the profit of any technology. So yes, the answer, or the short answer for your question is yes, certainly we need certain type of preparation for biomass to handle it easy in a fluidized bed gasifier on a gasifier.
Thank you.
Thanks, Bob. Samy, another question. You were speaking about using glycerin in your unit, and I'm wondering, what do you think the potential for glycerin using it in the unit is, and how successful has it been? How efficient is the conversion there as well? Is it higher than biomass, perhaps?
Thank you, Leif, for your question. That's a very important question here, and it's facing many plants currently working in biodiesel production. Certainly, if I have a biodiesel plant and I'm using vegetable oil to produce biodiesel, and certainly we are producing glycerin as about 10% in terms of weight compared to vegetable oil. So we are producing glycerin in biodiesel plant, and if I'm using my initial material, vegetable oil, glycerin has almost 1,000 of use to use it. On the other hand, if I'm using animal fat to produce biodiesel, so if I take animal fat blended with methanol or methoxide and producing biodiesel, we produce glycerin, and this glycerin cannot be utilized in pharmaceutical use because several groups consider it non-kosher because it comes from animal fat. So the option we currently have now is just burning glycerin, and burning glycerin in a wrong temperature. What I mean by wrong temperature, in a lower temperature can produce a toxic gas named acrolein. Acrolein is a toxic gas. So if I take the glycerin coming from a production of animal fat mixed with methoxide, which produce glycerin, and then I'm gasifying this under a controlled environment, it can produce higher BTU gas or medium BTU gas, and then this gas certainly can be burned and generate steam. Steam can drive the turbine, and the turbine can generate electricity. So the biodiesel plant, instead of burning the glycerin out in a chimney to the atmosphere, no, they can gasify it, and based on the BTU of the gas, they can start generating some electricity, which I think it can put them partially independent on the grid. So that was the main idea of this project, is to take the glycerin, crude glycerin, and gasify it to produce mainly producer gas, which has a little bit higher than 125 BTU per cubic feet.
Great, thank you. Is Steve on the line, and do you have a question, Steve? Or I could read it here. I'll go ahead and read it. Samy, would you mind comparing?
I can read the question here, so if you can.
Okay. Would you mind comparing torrefaction with pyrolysis and what the difference is between those two?
Sure, yes, yeah. Pyrolysis, we have different type of pyrolysis process. I mentioned here a fast pyrolysis, which I mentioned I need 1,000 degrees centigrade rise in each minute. So I need to take my biomass and instantaneously heat it up. That's a fast pyrolysis. We have a slow pyrolysis process. I can take the biomass and in a very slow heating rate, I can convert it mainly to char. On the other hand, torrefaction, I can take my biomass, expose it in a temperature in the range of 300 centigrade, and keep it maintained in this reactor for longer time, about 30 minutes, and this will produce more char. So the major difference in the operating parameters, fast pyrolysis, I need very short residence time, I need biomass to have exposed to a high heating rate. In a slower pyrolysis, I will expose my biomass to a longer residence time compared to fast pyrolysis, and also a lower heating rate. Torrefaction, on the other hand, I'm exposing my biomass to a lower temperature, 300 degrees centigrade compared to 500 in fast pyrolysis, but in a longer residence time. My major goal, my target for pyrolysis is bio-oil. My target for torrefaction is char. So in torrefaction, all what I'm doing is when I expose my biomass to 300 degrees centigrade, certainly I'm taking all the moisture out, and then I'm taking some of the carbon dioxide in the biomass or the volatiles in the biomass, which can be released as carbon dioxide, which maybe will enhance the BTU of the biomass. I'm not creating energy, I'm decreasing the non-combustible volatiles from the biomass, so per pound basis, my biomass BTU will increase in torrefaction. So the main difference here is the target. In pyrolysis, I'm looking for more crude oil, similar bio-oil. In torrefaction, I'm looking for more char produced.
Great, thank you. One more question. What are some of the considerations for sourcing biomass? You talked a lot about efficiency of conversion, and how does some of the sourcing of the biomass from the field, let's say, or from the region, how does that affect the energy rate of return or kind of total system efficiency of these units?
I think personally I see that we can have a source of biomass as one of the parameters which can affect any kind of a major center or a large centralized process, because to find different type of varieties of biomass that can cover all year round, so it will be a major issue. And also the condition of the biomass which we are collecting from the field. So regarding the source of the biomass, I think if we start building more machines, more reactors that can handle wide varieties of biomass, it doesn't mean that only my system here. No, I don't mean that. I mean more varieties of biomass can be accepted to be handled with different type of reactors, then this all together can work on converting different type of biomass to fuel or more value-added chemicals, which I like just to mention here within the answer of your question, that it does not mean that because I'm giving a presentation about gasification and pyrolysis, I will at any moment mention that this is the technology which we need to use. No. My goal is to promote all the technologies we can depends on the source of biomass. Like if I have liquid manure, I will go for anaerobic digestion straight. It will be easier than drying and gasifying the material or burning. If I have a sugar source of material such as corn, I will go through the fermentation. So all the technologies will work together to start producing or covering all our requirements of the amount of oil or liquid fuel, which I mentioned earlier. And regarding maybe transporting or taking the machines to the field, that's my own personal thinking, which I hope I'm right on that track, that instead of building a large unit, a larger number of smaller units can handle the biomass maybe easier. That's my own personal thinking, which I'm hoping that it will be on the right track.
Great. Thank you, Samy. Thanks for your excellent presentation. If any of our listeners have further questions, I encourage you to get in touch with Samy directly. On behalf of the Energy Training for Agricultural Professionals program, thank you for participating in today's webinar and have a great day.